Hi everyone, this is Anna Bergstrom here, and we are just going to do a quick review of the basics of acid and bases. So, by the end of this video, you should be able to describe what constitutes an acid and a base, describe the difference between weak and strong acid, state what conjugate bases and acids are in a reaction, and use pH and pOH scales to summarize acid and base status of environmental waters. So, first off, what is an acid and what is a base? In the context of chemistry, it is neither a musical instrument nor a thing in a sports ball game. For a base, and for an acid, it is not a thing that a kindly lady on a bicycle would hand you in the desert. Instead, we're talking about substances in water most frequently. So for acids, it's what you typically think of as coffee, lemon juice, vinegar, and on the bases, it's more of things like ammonia and lye. If anyone has seen the movie Fight Club, you'll know that bases and lye can be just as nasty as some of these things like battery acid. So, key concept. There's tons of ways that you can describe a acid and a base, but we're going to use the Bronsted-Lowry definition of acids and bases. Of course, it's two old white men hanging out at some point in history, and their definition that they came up with is an acid is anything that donates a proton, and a base is anything that accepts a proton. So one thing that you need to know is water is the most common acid and base. It serves as both. So if we have two waters, they can dissociate into the hydronium ion and the hydroxide ion. So we have a positive for our hydronium and a negative for our hydroxide. And something that you need to know is hydronium is always in water in that form. It's always H3O plus. However, turns out that people are lazy and writing H3O plus is just too much to handle. So you will see it frequently shortened to H plus, or you'll hear people talk about protons in solution. And in reality, what it actually is hydronium and not just H pluses floating around out there. So, water can serve as an acid. For example, if you have water, you add something like azonide, what you end up with is your hydroxide ion and ammonia. So in this case, water donated a proton to azonide and made ammonia. Water can also be a base. So again, we have water, we add something like hydrochloric acid to it, it turns into our hydronium ion and chloride. So in this case, water stole this proton out here, added it to H2O to make this hydronium, and we were left with chloride ions in solution. So that's how water can be a base. One thing that you need to know is not all acids and bases completely dissociate, like we saw with hydrochloric acid in that last example. So we can have strong acids, and those are by definition one that completely dissociates, and we can have weak acids, which do not 100% dissociate. We can also have strong bases and weak bases. So same definition, just apply it to bases. So, for example, we can have a strong acid. So hydrochloric acid, like we saw just a couple slides ago, completely dissociates. So we have this hydronium. We have a proton that in water becomes hydronium, and then we have our chloride ion. We can also have a weak acid. Acetic acid is a good example of a weak acid. So we start off with acetic acid, we end up with a free proton, and we end up with propiolic acid as a product of the dissociation of this weak acetic acid. Similarly, we can have strong and weak bases. So calcium hydroxide is a strong base. We start out with calcium hydroxide and we end up with calcium ions in solution and 2 hydroxide ions floating around in solution. Similarly, we can have a weak base. So ammonia is a good example of a weak base. If we add ammonia to water, we can end up with ammonium, NH4+, and a hydroxide ion floating around. So for every acid, there is a base. These reactions are frequently reversible. So if we have a weak acid, like hydrofluoric acid, we can have a weak base, which is our fluoride ion and our proton here. So a conjugate acid is a species formed by the acceptance of a hydroxide ion, and a conjugate base is a species formed by the acceptance of a proton. So So in this case, for our ammonia, our acid here, our conjugate base is ammonium because it accepted the proton. So we can have more than just the gain or loss of a single proton. We can have polyprotic acids. So some acids can donate more than one proton. So for the example of sulfuric acid here, H2SO4, in water, we can have a free proton or hydronium, and we can have HSO4 minus. That would be the first step, and then we have the second step where our HSO4 minus donates a second proton and becomes sulfate ions in solution. So in this case, sulfuric acid is diprotic. It lost 2 protons along the way. Similarly, we can have triprotic acid. So phosphoric acid here, H3PO4, can lose all 3 protons and become phosphate ions in solution. So we can have monoprotic, diprotic, and triprotic acids. But how acidic or basic is it? We've so far just talked about losing single or up to 3 protons. We can use the pH scale to determine how acidic or basic some solution is. So in plain English, the definition is a measure of the strength of acid or base character of some substance. So in math, what this is, pH is the negative log of the concentration of protons in solution, which, keep in mind, it's actually the negative log of hydronium ions in solution. Similarly, pOH is the negative log of the concentration of hydroxide ions in solution. So this, if you come back to thinking about what we learned in thermodynamics and our equilibrium constants, we can have a constant for the dissociation of water, Kw. And that Kw at 25 degrees C is 1 times 10 to the negative 14th. So if you remember, if we have 2 waters, it can dissociate into hydronium ions and hydroxide ions. And we can simplify this down into H2O equals H plus OH minus. And so if we use this equation and the definition of what an equilibrium constant is, keep in mind our water is a pure liquid, so that kind of cancels itself out, but we do have the concentration of hydronium ions and hydroxide ions in our solution. And our Kw here, remember, is 1 times 10 to the negative 14th. So if we go over here, we have 1 times 10 to the negative 14th times the concentration of H plus times 1 times 10 to the negative 14th equals the concentration of H plus times the concentration of OH minus. If we take the negative log of both of those sides, what we end up is the water dissociation constant equals pH plus pOH, which you'll remember is the concentration of the negative log of the concentration of hydronium and hydroxide ions. And if we know that they're in perfect equilibrium, in this case, if we have pure water and it was 1 times 10 to the negative 14th, that is 1 times 10 to the negative 7th for each of these. And if you take the negative log of that, that is 7. Hence why a perfectly neutral pH is 7. So if you've always been wondering why 7 and 14, now you know. So let's do a quick example of using the pH. So if the hydronium ion concentration of vinegar is approximately 4 times 10 to the negative 3 molar, what are the corresponding values of POH and pH? So pH, again, is the negative log of the concentration, and in this case, our negative log of the concentration of hydronium ions is 4 times 10 to the negative 3. So our pH is 2.4. Similarly for POH, we know that we have 14 minus 2.4 is 11.6. So our POH is 11.6. So that's all I have for you, and we will pick it up back up in the next lecture with more acids and bases.